To determine whether a function is even or odd, we have an algebraic test that stems from what's happening on the graph. If we were to consider a graph symmetrical about the y-axis and an ordered pair xy, we see that plugging the value negative x into that function would give us the same output y value. So both negative x and positive x yield the same y value, and that essentially is going to be the algebraic test that we use in order to determine whether or not the function is even. If the function evaluated at negative x, which is a y value, and that's the same y value that we get when we plug positive x into the function, this is an even function. And if this is true algebraically, then it's true for all x inputs throughout the entire domain, and then that would yield a even or symmetrical about the y-axis graph. An odd function is one that has symmetry about the origin, which means essentially that if I were to put a pin in the center of this graph and flip it upside down, we would get the same image. When we consider an arbitrary point on a graph that is symmetrical about the origin, we notice that when we plug the opposite of that original x value in, we also get the opposite of that original y value. So coming out some distance in the direction of x, we get some distance in the direction of y. If we come out the same distance in the direction of x except for negative, we see that we get that same distance in the direction of y, but this time again also negative. And this becomes the algebraic test to determine whether or not a function is odd. When we plug the opposite of x into the function, we get a y value that is the same distance in the direction of y, but in the negative direction instead. So if those y values are the same measure but opposite in direction, then we get a function that is odd or symmetrical about the origin. And this algebraic test basically says that it's true no matter what x value I plug in. This was an arbitrary x value. So if this is true for all x's, then we have a function that we say is odd. And so just to summarize, we're essentially going to plug negative x into the function and then determine what the outcome is. If that simplifies down to being the same as the original function that we started with, then we'll say that the function is even. And if that simplifies to being the exact opposite of the original function, then what we have is a function that's odd. Let's look at a quick example here. We're asked to algebraically test for symmetry, which means that we want to use the test where we plug negative x into the function. So since we're plugging something in for x, we're going to open up holes for those x variables. That's negative x to the 6th power 4x squared minus 2. And into those variable spots, we're going to plug negative x in. Now we simplify. Order of operations says that we need to deal with this exponent first, so we'll have to wait on this negative, just bringing it down. Negative x raised to the 6th power is x to the 6th. And again, we'll square negative x here to get 4 times x squared positive now, and then we still have the minus 2. So continuing to simplify, we have negative x to the 6th plus 4x squared minus 2. And we'll notice that that's the exact same function that we originally started with. So when we evaluated this function at negative x, we got the same as the original function, which means that this function must have been even, which means that its graph is going to be symmetrical about the y-axis. And now to check our answer, we can come over to the calculator and plug in the original equation by selecting y equals and inputting negative x raised to the 6th power plus 4x squared minus 2. And then when we go over to the graph, we see that our graph does appear to be symmetrical about the y-axis, which supports what we found algebraically. And now in part B, we'll do the same thing. We will plug negative x in for the x variables of the g function. And we do that by opening up holes for those x variables. So that's x to the 7th minus 3x to the 5th power plus 2x cubed minus 1, and then we plug negative x in for all of those x values. And so g evaluated at negative x becomes negative x raised to an odd power is going to be negative x to the 7th power. Again, we need to do the exponents first, so we have this minus 3 that's just waiting, and negative x to the 5th power is again going to remain negative, so that'll be negative x to the 5th like this. We raise negative x to the 3rd power, so we have plus 2. Negative x cubed is negative x cubed minus 1. And then continuing to simplify, we have negative x to the 7th. And now negative 3 times negative x to the 5th, that's going to be positive 3x to the 5th power. And 2 times negative x cubed is going to be minus 2x cubed. And then we still have minus 1. Now, when we compare this back to the original equation, we can see that g at negative x is not exactly the same as the original function. So let's then consider what the opposite of g of x would look like and see if what we obtained is the same as it. The opposite of g of x is going to be the opposite of the entire original function, which is x to the 7th minus 3x to the 5th plus 2x cubed minus 1. So the opposite of the original function would be changing the sign on all of the terms. When we distribute in that negative, each of those terms gets a sign switch. So we already determined that g of negative x was not the same as g of x. Now let's consider to see whether or not g of negative x is exactly the same as the opposite of g of x. The g evaluated at negative x function now compared to the opposite of g of x, still these are not the same, right? Because we have a minus here and a plus here. So no, they're not the same here either. So since g of negative x was not the same as the original, nor was it the same as the opposite of the original, we'll say that that function g is neither even nor odd, which means that we can expect for that graph not to have any symmetry. And now again, to check this answer, we'll go over to our calculator selecting y equals. We'll need to plug in the original equation, x to the 7th minus 3x to the 5th plus 2x cubed minus 1. And then when we come back over to the graph here, we see that we do not have symmetry about the y-axis. And if we were to rotate this graph upside down, essentially turning the calculator upside down, we would not get the same as the original graph. So this supports our algebraic finding that the function g of x has no symmetry.